And today we have a lot of material to cover. So let's start with the outline. This is the second lecture of our course. So we'll start with some material about hierarchy of transformations. And then we'll speak about the difference between calibrated and uncalibrated camera. This yields to the issue of projective versus Euclidean reconstruction. We'll study how to calculate a camera matrix. And then we'll speak about, maybe if time left, we'll speak about some recent work about retrieval of camera pose. Okay, so let's start with the issue of hierarchy of transformations. So what is projective transformation? A projective transformation is invertible mapping between the projective space, the P2 to P2, such that any 3 points that lie on the same line, if and only if the mapping of them lie on the same line. This is the definition. Okay. In a minute, you will see why projective transformation form a group. It means that the projective transformation have an inverse, and the composition of two projectivity is also a projectivity. In a minute, you understand why. Okay. Essentially, it can be shown, and we'll prove partial of this theorem, that a mapping is a projectivity if and only if it can be described by a non-singular matrix, which is 3 by 3 metric, such that the mapping can be written as some linear transformation, h times x. Okay. Why is it true? So let's try to do the one direction. Essentially, we'll show that if H is non-singular 3 by 3, then it's a homography or projective transformation. The other side is more involved, and we will not show it. So let's follow the definition, and let's take 3 points that lie on a line. If you remember from last lecture, if a point lie on a line L, it can be the dot product between the representation of the line and the point is equal to 0. So if H is non-singular matrix, then we can insert here inside H minus 1 times H, which is identity. And then we see that the points H, X, Y lie on the line, which is determined by L transpose H minus 1, which is actually H, the inverse of H transpose time L. So this is a very simple direction. And we have shown here that actually that any non-singular matrix 3 by 3 is homography. Okay. In general, you can determine homography in the following way. Can I ask to mute? Okay. In general, in higher dimension, we can actually have the definition that homography between the projective space of dimension n to the projective space of dimension n is actually an invertible mapping between x prime and x. Okay, this is the way that you can define it. Okay. Let's try to understand why projective transformation are important and where we get projective transformation. So actually, this is the 3D world, and this is some plane in the 3D world, and this plane is mapped to the image plane. Essentially, the mapping, the perspective mapping between this plane and this plane is actually can be determined by homography. I guess that those of you who took the course in computer vision in the previous semester already know this observation. Another situation when we tackle homography, let's say that we have a planar surface, and let's say the planar surface is two images, image 1 and image 2. Then we know already that from image 2, from the planar surface, it's homography, and from the planar surface to the image 1 is also homography. And concatenation of homography, it's an homography. So the relation between image 1 and image 2 is also homography. Can be determined by homography. Okay. Also, another situation that I guess that you already studied in the course in the previous semester is that when you have a camera and you just rotate without translation around the camera center, then the relation between the two images captured by before the rotation, after rotation are related by homography. Okay, let's move on. Let's see an example. So we just say that if we have a plane and the plane is captured by two cameras, the left camera and the right camera, then the way that we can move from one camera to another camera is by homography. So if, like this, if I have some points in the world which reside on the plane, and one camera is captured, the left camera is captured the image, and we denote the coordinate on the left camera by xi, and the right camera, P2, captured the image, and we let the coordinate on the right camera to be yi, then according to what just said, there is an homography such that xi is related to yi by homography. Okay, we've just seen it. Okay, so let's try to calculate how many degrees of freedom do we need in order to determine the homography. So homography, do you remember how many? If I have a homography between 3 by 3, do you have an idea how many degrees of freedom do we have? We have a matrix of 9 elements, and how many degrees of freedom do we have? Anybody know? Anybody?
8.
Sorry?
8.
8, right, exactly. Because the homography is determined up to scale, and we have 8 degrees of freedom. Okay, let's calculate how many equations do we have. So we have, let's say that we have n points, yi, which are transformed to the point xi. Okay, we move from here to the right to the left. So by the relation that xi is related to yi by homography, actually we need to solve the equation lambda I times xi equal to hyi. So each pair of xi, yi contributes exactly 3 equations. So in total, we have 3 n equations, and we have 8 degrees of freedom coming from the homography, and n degrees of freedom which came from what? Why would you have an extra n degrees of freedom? Anybody know?
The lambda I value?
Exactly, yeah, lambda I. Lambda I extends the number of degrees of freedom by n. Therefore, we have 3 n equations and 8 plus n degrees of freedom. Therefore, n actually should be greater or equal to 4. Okay, so let's see.
What n stand for?
N stand for is number of pairs that you know that, like for example here, x1 is the same point like y1. X2 is the correspondences and enumerates the correspondences. Okay.
Okay.
Sure.
Can you turn on your camera also on Nadav, please?
Okay. So this is the resulting homography that was computed in some way. Later on in the course, you will understand how to calculate the homography. And as you will see, after calculating the homography and on yi and applying the homography on y, you get actually the same plane that we see on the left, we see now on the right. And when you take the two images and we put them one on top of the other, that's what we get. It seems that the points on the plane really seem to agree. However, what happened in the environment? Why the environment is not coincide in the two images? Do you have any idea?
We didn't transform, no?
Sorry?
We didn't transform the x's to y's.
Exactly. I mean that the homography acts on the plane and not on something which is, it's not a plane, okay? And we just take this specific plane and calculate the homography of this specific plane. Right, okay. So far we talked about homography, and let's now talk about special cases of homography, of projective transformations. And actually, these special cases of projective transformation are especially in the following thing. We write the transformation by blocks, like here, okay? A is n by n block. But it's very important to know that the last row is actually paired by 0, and the last entry is 1. Here we have a vector, which belongs to Rn. Now, due to this relation, that the last row is written like this, actually, we speak in the projective space Pn, but actually we can simply immediately transform it to the Euclidean space due to this relation. Since any how you say, any homogeneous coordinate given in Pn is actually transformed to another homogeneous coordinate given in the respective space of the Euclidean space, but due to this 1 and 0, the last entry of the coordinate does not change. It stays 1. So it's actually easy to think about it like this. So if we speak about affine transformation, by the way, how many of you are familiar with affine transformation? Nobody did. Okay, so affine transformation actually is like linear transformation plus some translation, like here. So if you think about it in Rn, it's take the vector multiplied by some matrix, which is invertible, and add some translation. And in block format, it can be written like this. Okay, another thing that can be said about the affine transformation is that it preserves parallel line, like you see here. You move from here to here, parallel lines are preserved. And also, but as you see, the angles, for example, are not preserved. But also, line at infinity, the line at infinity, if you have some coordinate in infinity, it stays at infinity, and you have some coordinate which is finite, it stays finite. This is due, actually, to this last row. In an exercise, you later on will ask to show that essentially only the affine transformation keeps the line at infinity at infinity. For example, general homography does not do it. So later on, you'll get an exercise for it. Okay, let's move on. Here we have similarity transformation. It's more restricted transformation. R here, it's rotation. S is some scaling bigger than 0. Actually, this is a special case of the affine transformation. Here we have the preservation of parallel line, but also here the angles are preserved. Okay. Okay, let's move on for the next transformation. So here we have what we call the Euclidean transformation, or the rigid body transformation. And here, actually, we have just the rotation and the translation, no scaling. This is a special case of the similarity transformation. And the idea here is that this transformation preserve the distances between the point, does not scale the distances between the point. Okay. Okay. Sorry. So I'm not going to read the exercise, but here you see that you will ask to show that the light at infinity, and infinity is a fixed line under the projective transformation H if and only if H is an affinity transformation. It's not difficult to show it. Okay. Any question before we move on to the next topic?
Yes, I have a question.
Yes.
Can you give some intuitive explanation as to what might cause an affine transformation, just like you gave for homographies?
Yeah. For example, any a plane, okay, that you just a minute. Yes. Any plane, for example, that you see from here, for example, you take a plane and you take the plane and you apply some transformation in this plane, for example, and that's what you get. For example, think about take a mesh of triangles, for example, and make some deformation to this mesh, for example. Okay, and each triangle in this mesh is going to have some affine transformation that can be determined to this specific triangle. This is, for example, in plane transformation. Okay, let's move on to the next subject. I would like to, I think that last time I missed something that was very needed to understand the structure for motion problem. I would like to make some, to say a few things that will let you understand the situation more than the last time, because I think I missed maybe some intuition last time. So I would like to try to understand the structure for motion problem from this illustrative point of view. Say, if you remember what we said, we said that the structure for motion problem is such that we have images like this, and we would like to reconstruct the 3D object and the location of the camera. So let's try to understand it visually. So I have some 3D object in the space. I don't know the location of the 3D object. What I know is the following. I know that I have these 3 images, and I know that, for example, this red point and this red point and this red point, somehow I know are coming from the same 3D point in the space, but I don't know the 3D point in the space. Okay. Moreover, each a point in each image is given in its local coordinate. Sorry, just a minute. It's given its local coordinate system. Essentially, each camera has its local coordinate. Okay. The idea is to try to understand how to move from this different local coordinate system to some global system, okay, such that I'll be able to understand what is the structure of the 3D object that I'm looking for. And for that, to that end, I need to understand where are the cameras. Having this, I can triangulate, like you see, like here, I can take the rays from the center of the cameras and get the 3D point. And this allows me the move from the global coordinate system to the local coordinate system, allows me to understand how to create the 3D structure in some reference global coordinate system, because what I see is only the local coordinate systems. I hope now it's better than last time, because I wasn't sure that this would deliver last time very clear. Okay. So, okay, any questions?
The 3 cameras is just for illustration. You don't really need the 3. It's enough. It's sufficient to use only 2, right?
Yes, yes. But you know, this course relies on some multi-view setting and not just 2 cameras. And the idea is to get the idea from many cameras and not just 2 cameras. Okay. Okay. But your remark is really true. Okay, so let's try now to write it mathematically. So this is the same picture, now without the cube, just to say that we have n images, and we know that we have some correspondence between the images, like what we had before, the red point, the green point, etc. We don't know the 3D. Okay, what we know is only the following. We know on each image that the scene point J, we don't know the scene point J, was projected to the image I. We denote it by Xij like this. Okay. And then we would like to, this is the input, and then we'd like to determine 2 sets. One set is the set of the cameras, the projection matrices, and the other set is the set of the 3D point, M3D point. Okay, this is mathematically. Okay, now, just a minute, let me clear the drawings. Okay, now I'm just remind you that we spoke about the general camera P, which is K times R which is K times the block RT. Remember that RT moves me from the word to the local coordinate system, like here. We call it external parameter. And then we move from the word to the camera sensor, like here. And this is done by K. Okay? So we discussed it, and I hope it's clear now. So just want to remind you what is K. K has 5 degrees of freedom. I'm just trying to, okay. K has 5 degrees of freedom. We spoke about them. I don't want to repeat it. Just want to move on and to try to say something new that we just spoke about it, that want to remind you the following thing. So, okay. So we understand that now we have the point in homogeneous coordinate in the 3D space. We have the camera matrix, we have the projection, and we have some constant that we don't know him. Actually, what is if the input to the structure for motion algorithm is like I described before? What I know here and what are the unknowns? Anybody can say? From this, in these equations, what are the unknowns and what I know in solving the structure for motion problem? Try, it's okay if you make mistakes, okay. Just
I think we want to know the true 3D coordinates. So it's the big X is unknown. We know P, the camera matrix.
We don't know P. We don't know P. We also want to know it, right? This is also unknown. And what we know?
Okay. We know X.
Exactly. We know X, and we don't know also lambda, which is some slack variable, I would say, something that is a byproduct that we'll discuss it later on also. Great. Very good. So this is the camera equations. And now there is a difference between 2 kinds of camera. A camera, which is 3x4, as you know, which is written like this, okay, is called calibrated if the inner parameters K of the camera are known. Why is it so important? Because if the the inner parameters are known, I can move on now back to the 3D space, and I can move on now to work with length units and not in pixels. And actually, what essentially we do, we multiply both sides of the camera equation by the inverse of k, and then we say that we have the normalized coordinate x tilde, and we solve only for RNT. Okay, just we solve, or just want to say it. Okay.
Miraf, can you clarify again? So x without tilde is image coordinates. So it's
exactly
like
x without tilde is in pixels.
And x with tilde is in the local coordinate of the camera.
A local coordinate in the world, I mean in metric space, I mean length unit. Okay.
Yes.
Sure.
Okay. Mm-hmm.
Okay. Good question. Okay. Okay. So let's move on. As I said, the new camera RT is called normalized or calibrated camera, and x tilde are called the normalized image point. Okay. Okay. This is not just a definition. This is very important. Why this is very important? Because when I'm going to make the reconstruction of the world, when I have an uncalibrated camera, I can have projective reconstruction. In a minute, you'll see what I mean by this. When I have calibrated camera, I can have Euclidean reconstruction or metric reconstruction. Visually, it seems like that. On the left, I have the projective reconstruction of the Arc of Triomphe in Paris. On the right, I have the Euclidean reconstruction. Essentially, this reconstruction on both sides have the same error, but the left side seems strange and the right side does not seem strange. This is visually, this is the difference between the projective reconstruction and the Euclidean reconstruction. Now, let's try to dive in to understand why we have these differences. Okay.
There is no way to calculate the k.
There is, and we'll in a minute you will see, and not a minute, but a few slides later, and later on the course we'll speak about it. There is. Okay. It depends on
What does it mean?
Yeah.
What does it mean that like they have the same loss? Because the projective one looks bad, so I guess it's a bad result.
Okay, there is something which is called reprojection error, and then reprojection error you measure giving the cameras and the 3D point that you calculated. You measure how your algorithm calculation is related or it's close to the point that you see in the image, to the correspondence that you see in the image. And this difference, then we'll have many lessons about it. This difference is called the reprojection error, and I mean that reprojection error is in the same order, on the right, on the left. Okay. Okay. So let's continue, and
Merav, can you please explain like a little bit more about the differences between the two here? Like, how is it so like the performance here is really like you can see it. So
let me continue, and you will see exactly why there is a difference. Okay, let me continue, and in 4th slide, I think to understand why there is such a difference. Okay.
Okay. Thanks.
Let me continue. So I'm repeating this. We are going to solve the structure for motion problem, and we have what we have. It's the image projection xij. That's what we see. That's it. And we want to determine the 3D scene and the metrics. That's what we said before. Just recall that I stands for the image I, and J stands for the point in the space, just to be consistent. Okay. So, okay, what is going to happen with the projective reconstruction? Now, the calibration metric is unknown. P is 3 by 4. Actually, any 3 by 4 metrics with left block, which is non-singular, can be matrix, camera matrix, sorry. Now, I want to show you that the solution of the projective reconstruction is unique up to some projective transformation. Why is this? And this will answer your question. So assume we have some solution. PI, I already know the cameras and I know the point in the space. So it means that I know how to solve this equation. Okay, this equation is solved. Okay. Now, what can I do now? I can take some homography, any homography between P3 to P3, put it between PI and XJ. This is just an identity, right? And what happens now? What happens now is that I have a new set of cameras, a new set of points, like this. The points in the space are some homography times XJ, and the cameras are the inverse of homography from the right times the camera that what I had before. This explains the distortion or the way the projective reconstruction seems in what we saw before, right? Essentially, lines will be lines, etc., etc. But the distortion is due to the degrees of freedom of the homography. So if I have homography between P3 to P3, how many degrees of freedom do I have? It's a matrix 4 by 4, right? How many degrees of freedom I'm going to have? Anybody knows?
What's a matrix of 4 by 4?
Sorry?
Again, what's a matrix of 4 by 4?
Okay. You see, we have homography, and the homography is applied to a coordinate, which the size of the coordinate is 4, right? So H is 4 by 4, right? And H is homography, right? And I introduced here H that distorted the point and distorted the cameras, right? And I have now new cameras and new points in the space with the same projection. I didn't change the left side, exactly the same projections, right? So I can take some situation and try to and move it to another situation by introducing homography such that I'm changing the cameras and the points. Okay, and I'm asking how many degrees of freedom I have in this ambiguity of the homography, which is 4 by 4. Anybody knows?
15.
I don't hear you well, sorry.
15.
Exactly, 15, right. Okay, so
but don't we want that this H take the last coordinate, which is 1, and keep it 1?
this will be how do you say, will be attenuated in lambda in lambda ij. Okay, lambda ij will be different, but xij will be the same. Okay.
Rav?
Okay.
You're saying that this is happening because we don't know the calibration matrix, but if
Right.
it is known, so why we can't plug in the h times h minus 1?
Okay, if it is known, let's go to the next slide. Very good question. But if it's not if it's not known, that's what I can do. I have 15 degrees of freedom, and I can distort the view, and I can change the camera matrices. But let's go to your question, which is the next slide. Okay? By the way, this is just another example to let you understand that, by the way, this is in the Euclidean space, the construction in the Euclidean space, and this is done in the projective space. Many, many options, okay? Now, let's say that I know the calibration metrics. And let's see how does it help me to remove the projectivity ambiguity that we had before. So, as we said before, we normalize the image coordinate, okay? And now we have the new camera equations, like what you see here. And my next question is, if I'm going to insert here homography, like what I did before, does it okay? Do I have the same situation as before or not?
No, because you lose the rotation and translation.
Exactly, very good, great. So I cannot do it, okay? So
Explain it in more details. This was exactly.
yes, I'll explain in more detail. Yes, sure. Can I do the same trick as before? And the answer is no. Why? Because if I multiply some rotation and translation by some general homography, I'm not necessarily going to have a rotation again. And if I want to be in the Euclidean space, I want to determine the camera metrics with respect to rotation and translation. And if I'm multiplying by some general H, I'm destroying this requirement. R is not necessarily anymore rotation metrics.
But
okay?
In the last slide we had P, and P is exactly R and T, no?
What is it?
In the last slide, we had P times xj, whereas P is exactly this, R and T, isn't it?
Yes, P is R and T in the Euclidean space.
So why before we didn't say that we can't put an H because it destroys the rotation?
Because in the projective space, okay, just a minute. In the projective space, P can be any matrix. 3 by 4, any matrix is not singular in the left block. This is exactly the difference between general P, which had 12 entries, and some constrained camera matrix, which should consist of left block, which is rotation. Okay, sure. Let's move on.
I have another question. So what here in Euclidean reconstruction, we're still inserting like the identity matrix H times H inverse. Why can't we do that? Because it's just the identity.
What is H? What is it?
Some general homography. Why can't we insert the H times?
It will change the rotation.
Yeah, but it's still a valid operation to insert the identity matrix in between, right?
Right, but this is not the ambiguity that you get. Let me show you exactly what kind of ambiguity you can still take into account. So you can take a special case of homography, which is the similarity transformation, like what we have here, which is written like some scaling times a rotation matrix, some vector in R3, 0 and 1. As you remember from the start of the lecture, this is exactly a similarity transformation. And let's see why this is okay, why this ambiguity is okay, why it keeps the rotation. Okay, sorry for that. So if now I'll take this special homography and insert it here, okay, what do I get? I get that if I divide this H by S and move it to the left-hand side, I get exactly this matrix. On the right, I'll get exactly this this modified points, okay? And now, as you see, I don't have the problem that I have before. Why? Just a minute, because now Ri multiplies Q and rotation by rotation stays rotation. Therefore, I'm getting the following new camera matrix. Ri times Q, which is rotation, new translation vector, a new set of points, which is actually can be said as a global translation and rotation and scaling of the situation. So by introducing a similarity transformation, which has 7 degrees of freedom, I moved from ambiguity with 15 degrees of freedom to 7 degrees of freedom. And as you remember, this similarity transformation does not distort the situation. it keeps, it does not preserve the distances, but it keeps the lines, it keeps the angles, etc., etc. This is the reason why the Euclidean reconstruction seems so nice and not distorted. Okay.
And
Can you
this is
just write?
basically,
Yes.
this is basically defined by our global system, coordinate system, isn't it? It's like
What
if
is
you
that?
apply some, like
This
this
is
similar.
global to all
So basically, it's the same as just like having a similarity transformation on the entire global coordinate system.
Exactly. Yeah. Let's
So
move
like
on.
if we put,
Let's move on. Sorry, because we have a lot of material to cover. Let's move on. If you want, you can take the things of all. Let's move on, please. So let's recap the differences between the projective and the Euclidean reconstruction. So in the projective space, we have projective ambiguity, and in the Euclidean space, we have similarity ambiguity. We saw it. The first one do not preserve angles or parallel line. The second one preserve angle and a parallel line. This is the reason that we see the visual reconstruction so nice. In the first one, the reconstruction looked distorted, as we said, and actually in the Euclidean space, the entire reconstruction can be rescaled, rotated, translated, like what you said just a minute ago, and this look very nice and metric. Okay, so let's move on because we have a lot of material to cover. So I'm going to speak about another issue. I'm going to concentrate now on a single view, not on many images, and you will see why. We're going to speak on something which is called the resection problem. In the resection problem, you have a single image in some local coordinate frame, and somehow somebody told you by some measurement, the measurement of the 3D object in the world. So what I know exactly that the coordinate, for example, of this cube in the 3D object are given and known. I have some way to measure them, and I know the correspondence between the 3D and the 2D, and I know the coordinate in the 2D. And what I would like very much to do is to calculate the camera metrics in this single view. Okay? I would like to say the following. I have the correspondence between the 2D point and the 3D point, okay? And I would like to calculate the camera metrics. That's what I would like very much to do in the resection problem, okay? Is the problem clear? So I can move on.
Just to clarify, big xi are coordinates in a global world.
Exactly. Yes, good clarification, exactly. Okay, very nice. Okay. So application, online navigation, tracking, etc., etc. So in this algorithm, we have two steps. First of all, since we know the scene points, we don't have anymore the projectivity ambiguity that we had before because we cannot change the location of the point. And actually, from here, we are going to calculate the camera metrics by some algorithm, which is somehow a linearization of the equations. In a minute, you will see what I mean by that. So I have xi and xi, capital Xi, and I would like to calculate the camera metrics P, single camera metrics, and as a byproduct, I'll also get the lambda I, okay? Once I'll have this, you will see a way how to instruct from P the calibration matrix K. But let's concentrate first on the first step of the algorithm. So, okay, so we want to solve the resection problem. As I told you, exactly this is written here in a very clear mathematical way. And how many points do we need? Let's calculate it. So camera metrics has 11 degrees of freedom. We already know it. And we have, we'll take n correspondences between 2D and 3D. So we'll have 3n equation, 3 for each correspondence. And we have, as we said, 11 from the camera and n from the lambda i's. So 3n should be greater or equal to 11 plus n. So n should be greater or equal to 6, which means we need to have 6 correspondences between 2D to 3D in order to solve the resection problem, to find the camera matrix. Okay, now we are going to speak about an algorithm which is called DLT, direct linear transformation. It's a very useful algorithm, not just for calculating the cameras, for many other things in computer vision and other fields. And let's try to understand it and how to use it. It's very simple, by the way. So this is the camera matrix, and these are the unknowns that we would like to solve for. Each row is written by P1, P2, P3, etc. Okay, so we have the point in space, and we have xi, capital Xi and little small xi are given. Okay, now let's write the equations. Okay, just a minute. Okay, these are the equations. Each correspondence give me this set of equations. Lambda I times xi. Now I'm multiplying the first row by xi transpose and the second row by xi transpose, etc., etc. Look at the equation and see that this is known, this is unknown, this is unknown, and this is known. Essentially, I'm getting something like just linear set of equation. Let's write it in a matrix. It looks like this, okay? This is the unknown, P1, P2, P3, right? This is just columns, P1, P2, P3, lambda is its color. In total, we have 13. From each point, we have 13 unknowns. And this is the matrix. Like moving from here to here, it's very easy. And the right side is going to be, of course, 0, okay? This is just from one point. And if I'll have it, I'll have a collection of points, at least 6 points. That's what I'm going to have. I'm going to have a matrix, size of 3n. Each block of 3 is for 1 point, 1 correspondence. Block of 3n times 12 plus n, okay? Because I have 12 entries from the camera and n entries from the lambda i's. And this should be equal to 0, right? That's what we saw before. Now, you see that the matrix n is large. The matrix is very thin. It's long and in the rows direction and very thin in the column direction. And actually, what happens is that if the measurements is really exact, then the rank of this matrix is going to be at most 11 plus n, like what written here. And since I have, this is the number of columns, it means that the null space will be what size?
1.
1, exactly. And then I'll have a vector in the null space, and this vector in the null space will be the solution up to some scaling, of course. Okay, but in real life, the measurements are not clear and are not clean, and I have noise. So I have to somehow to solve the problem with noise. So okay, so so far we have the formulation, the matrix formulation, such that I want to solve m times v. V includes the columns of the camera matrix and the lambda i's. M include the measurements from the word and from the image. And I would like to get a vector in the null space of M up to some arbitrary scale, not the 0, of course, not the Fourier solution, such that this will be solved. And as I said before, if I have noise, I won't have, the null space will be empty, okay? Will not have an exact solution. So now we move to something which is very interesting, which is called homogeneous least square problem. Actually, in order to solve this problem, what you are going to do, we are going to write it in the following constraint optimization problem. I would like to minimize the norm of MV. MV actually it's a vector. and I want to exclude the 0 vector. So I would like to minimize it under the constraint that the norm of the solution is equal to 1. This is called homogeneous least square problem. Anybody familiar with it, with this problem?
Could you repeat why we require that the norm of V is equal to 1?
Because if we do not require it, essentially we'll get immediately the 0 vector, the trivial solution. I can require the norm of V equal to 10, never mind, but something that will move me from the 0 solution, right? Okay? This is the way we do it. Otherwise, I'll get the 0 solution. And I don't want to get the 0 solution. I would like something which is not the 0 solution. This is the way we do it. This is called homogeneous least square. Homogeneous is due to the issue that the right-hand side is 0. And actually, the solution of this problem is if you take the matrix M, you make singular value decomposition, and the last column of the right block of the orthogonal vector is the solution to this problem. And now I would like to ask if everybody is familiar with SVD, singular value decomposition, or I have to say a few words about this. Anybody is familiar with SVD, singular value decomposition?
Yes.
Yes?
Yeah.
Anybody is not familiar with SVD?
Can you just explain why V is the last column of V, capital V?
What is it?
Can you explain why V is last?
Yeah, sure. I'm going to prove it. Sure. Yeah, of course. Okay, just a reminder of the SVD in just a nutshell, that everybody will be on the same page, okay? As we have, symmetric matrices, and when we have symmetric matrices, we know, everybody knows that we can diagonalize the matrix into a set of orthogonal vectors times diagonal matrix, which contains the eigenvalues of the matrix, times the same set rotated of the same orthogonal vector. So, same set of the orthogonal vector. By the way, when I say orthogonal matrix, everybody knows what I mean by that? Just to repeat, an orthogonal matrix, a matrix such that, say, U transpose, U is orthogonal matrix, U transpose is equal to the identity. This means that the inverse of U is the transpose of U. Exactly like here, for example, you see, I have U, and this is U transpose. This is an orthogonal matrix because U transpose is the identity, and the inverse of U is U transpose. Okay. So in general, we don't have symmetric matrices. We have general matrices, and the SVD, the singular value decomposition, is a great way to factorize a matrix. So you have a matrix, not necessarily ribuit, just not a square matrix. You can have any matrix n by n, and you can factorize it into one set of orthogonal vectors and the other set of orthogonal vectors, and in between you have a matrix which is most 0, like here, but on the approximately diagonal you have this, what we call the singular value. So let's make it more concise and mathematically. So you take a matrix and you can factorize it into U, which is a square matrix, and V, which is another square matrix. Both of them are orthogonal matrices. And D, actually, the diag of singular vector, which we call sigma 1 to sigma p, ordered from the bigger one to the smaller one. Okay, D is not a square matrix. It can be also rectangular matrix. Now, if I order these singular values, what we call singular values, from the large to the small, it can be shown that if I denote R the last singular value that is going to be 0, then the rank of the metric is R, and the null space is spanned by the right orthogonal matrix VR plus 1 Vn, and the image of the matrix, okay, is spanned by U1 to UR, which is the left set of orthogonal matrix of the orthogonal matrix. This is very fast, I know, but we have to move on. So I hope you can anybody who is not familiar with the SVD can go over it and understand it. So,
Merav, can we take a break?
Yes, sorry. Let's take 5-minute breaks, okay? And sure, sorry for that. Yeah.
About the administrative stuff.
Okay. So let's move on and try to prove why the solution to the homogeneous least square problem is exactly the last column on V in the SVD of M. So let's decompose M in the SVD decomposition. Essentially, this is the constraint optimization problem that we are going to solve. So if I plug the decomposition of M into it, I'll get that I need to minimize U, D, V transpose V such that the norm of V is equal to 1. I guess that you know, it also can be proven very easily that if U and V are orthogonal matrices, then multiplying vector by orthogonal matrix will not change the norm of the vector. So this is exactly as minimizing. I'm omitting U from here and getting this, and I'm adding V transpose to here and I'm getting this. So this is exactly the same problem like this, because I'm not changing the norms. Rigid transformation does not change the norms. So let's denote V transpose V by Y, okay? So we need to minimize D, this is also Y, like this, dy such that the norm of Y is exactly 0, okay? Since dy squared is actually, because D, most of it are 0, and it has on the YAG pattern sigma 1 to sigma n, etc. Since dy is exactly sigma I squared yi, the summation of this, and y, the norm of y, needs to be 1, and since sigma I are ordered from large to small, then the minimum is obtained when I catch only the last singular value. And how I catch the last singular value? By putting zeros in y and 1 in the last entry. And this will let me have just the smallest singular value squared. Therefore, if this is y, and this is the relation between y and V transpose V, if I'll multiply this by V and V is orthogonal, I get that V equal to Vy. And since y is just 1 on the last entry, this V exactly captures the last column of the matrix V. Is it clear? Any question? Any question about this proof? Okay, so if somebody is not getting exactly the point, I guess that at home it's easy to show it and to understand it, but I hope most of it is understandable. Okay, let's take an example. It's time for examples. This is example taken from also lectures. So I have some scanning arm such that I can take this chair and get the 3D coordinate of the chair in many places. Okay, then remember what I would like to do. I would like to calculate the camera metrics. So in order to move on, if I have the 3D point, what I need more now
An image.
The image, and what in the image I need?
The same points.
The same point, exactly. I want correspondences. Great, good. So I don't have all the correspondences, but when I have feature point, like in the chair, these small holes, I can say that this is this, and this is this, etc. So I have 14 points for correspondences. Okay, so I can calculate the camera metrics, and I do it by using the DLT algorithm that we just said before. And now, because I have already the camera metrics, I can take all the 3D point, and project them on the chair, like here. Next, what can I do with this? This is okay. I can now take the 3D points and make triangulation, make a mesh of triangles, like here. And then I can take for each triangle the texture from the chair or the color from the chair. And then I can take this mesh, and now I can do the following thing. I can take the camera and change the camera and render new views from new cameras using this mesh, okay? So from my point of view, I see this. From my point of view, I see this. This is using the triangle and the texture of the triangles. So
The assumption is that each triangle is lying on the same plane?
yeah. This is the assumption, and you take the texture from the chair and you render, you make rendering. You just take and make it from different viewpoints. Okay.
What does it mean?
Question. Oh, sorry.
What does it mean, the texture of the chair?
I mean that in order to make the image with appearance, you have to say what is the color in this triangle, right? And you take the color for each triangle. You take the color from its projection on the chair. Okay.
There is a question from Nadav.
Okay, I'm sorry, I'm not sure that I see the questions. Can you please?
He's asking how would you do it when noise is introduced?
Exactly. If the noise is introduced, this is the situation. I'm solving the homogeneous least square problem because the null space is empty, and I'm getting a solution to this problem. This is the best that I can do.
I mean, for specific type of noise, but usually if you have outliers, it's a different type of noise.
Yeah, if you have outliers, this is not the situation.
We'll talk about it later in the
errors in the measurements. Yes, outliers is something else. Yeah.
Merav, what do you mean by triangulate?
Let's move on. But you know, when you have many ways to describe surfaces. You can use cloud of points. You can use voxels, and also you can use surfaces which are described by triangular mesh. This is what I mean by that. Okay. And there are ways to. Let's move on. But this just want to remind you that this is a possibility to make a use of this calculation. So we already know how to find the camera. Now I say that we are going to understand when I'm having the camera, how to extract the calibration matrix K. I'm hesitating if we have time to understand the normalization that has to be done in order to really get stable solution to the camera metrics. Maybe, I don't know if I have time. Okay, let's try to do it, and let's see if it's okay. Let's try to do it. I'm going to speak about the normalization that you have to do in any DLT algorithm or any algorithm that have different scales in the metrics, and in a minute you'll understand what I'm going to say. So before we do the DLT algorithm, we need to do some data normalization. This is resembled to what you do when you calculate, for example, fundamental metrics, if you know what I mean by that. This is not an option because this will affect the result. This is very necessary in this equation. And I want to explain why. So recall that the metrics contain the xi and yi, which are given in pixels. They can be hundreds or thousands. And also I have 1 in the matrix, right? This huge difference between this 100 or 1,000 and this one in the sense of magnitude. And why does it affect the result? Okay, I'll try to explain it. Okay. So in order to explain it, I would like to introduce a notion which is called condition number of a matrix. Anybody is familiar with condition number of a matrix? Okay. Yes. Oh, good. So I'll try that everybody will be familiar vaguely, at least intuitive in condition number of a matrix. So condition number of a matrix is the ratio between the largest singular value and the smallest singular value. And what does it stand for? What is the intuition behind this number? Okay. So if I have a large condition number, this affects badly the solution of the homogeneous least square problem. I want to say that a condition number, it's not a matter of algorithm, it's not a matter of accuracy of the computer, it's a property of the matrix. And if we don't handle it, you will get problems. Why is that? Okay, so in order to explain it, let's make it short detour and take a look at solving a system of equation. A times x, x will be. Okay, so what is the condition number? Let's say that B is distorted a bit. I have measure and B is distorted a bit, and I would like to ask myself the following question. If B is distorted a bit, how it would affect the solution? I mean that if A is known and B is known, and I would like to calculate X, if I'm distorting the bit, make some perturbation due to measurement, how does it affect the solution X? It turns out, okay, that if A has a large condition number, small change in B can affect largely the solution X. Okay, this is the problem. Okay, I mean that if the condition number of a matrix is large, when I perturb a bit the right-hand side, I get large error in X. And if the condition number is approximately 1, actually it can be no smaller than 1, the error in X is similar to the error in B. If I perturb a bit B, then X will get small perturbation like I got in B. And this is very important in solving linear set of equations. Actually, the condition number is the maximal ratio, the worst ratio between the relative error in the solution with respect to the relative error in the right-hand side. And it can be shown, not very complicated to show it, that the condition number is the largest singular value divided by the smallest singular value. The singular value is the singular value that we spoke before when we talked about the SVD. So in order to solve such problem, people use systems that are introduced to them a preconditioner, which is called P, and then instead of solving the original system, you solve this system. And if the condition number of P minus 1, the inverse of P times A, is significantly smaller than the condition number of the original condition number, then small perturbation will not harm anymore like what you had in the original problem. How does it relate to our problem? That's what I want to show you. Here we do not solve exactly a system of equation. It's similar. We solve something which is called homogeneous least square, where we know that the solution is the last column of the V in the decomposition of F of M to the SVD. However, it's very intuitive to understand. I will not prove it, but try to go with me and to say the following thing. This is the constraint optimization problem that I'm going to solve. But actually, this constraint optimization problem can be written as like this. I have a matrix M. This is the original matrix, and I'm looking for another matrix which will be close as much as possible to the matrix M, such that the rank of the new matrix will have rank 11 plus n. In this way, I will have something in the null space of M hat, and then I can solve the problem. Actually, this problem is equivalent to this problem. Okay. This is, by the way, Frobenius norm. It's the distance between two matrices. Okay. It measures how the entries of the one matrix are close to the entries of the other matrix. Okay. So since these two problems are equivalent, let's take a look on this second problem. It's more easy to understand the relation between the condition number and the normalization in this problem. Okay, let's move on. So this is the problem that you want to solve. Okay. Now, what is the objective of this problem? The objective is the square root of the sum of the square of all the entries, because this is the Frobenius norm. You take the difference between M and M star. Each entry, you take you square it, you sum over all these entries, and then you take the square root, okay? Now, recall that if M hat is going to replace M, this means that the entries of M will be changed. And how they are going to be changed? They are going to be changed such that this Frobenius norm will be minimal as such as possible, such that the rank of M star will be 11 plus n. Okay. However, recall that we have in matrix M xi, yi, and 1. Xi and yi, as I told you, are in pixels, so they are very large number. And I have 1, which is very small relative to this large number. Therefore, it means that changes such that M hat will be close to M would be such that, for example, if the term 1 is changed by 100, this is a huge change in the image point. But if the term xi is changed by 100 or yi, it's very slight change to the original problem, to the entries of the matrix or to the image point. This is the reason, and since M has very different scales of numbers, it has very large condition number, and therefore, when I'm going to solve it without normalization, I'm going to get very worse result. Okay? And how we are going to solve this problem? Actually, by introducing normalization. Normalization that I guess that most of you are familiar with it if you took the course of computer vision. And this is the normalization. You take the points, the original point, and you move it to the center of mass, like here. And then you scale it such that the point will be close to 1. That's such that so the variance will be close to 1. Okay, that's what you do. Just a minute. Sorry for that. Okay. So you as I told you, you rescale it so that coordinate will be roughly close to 1 somehow. That's the standard deviation. Many ways to do it. And then this actually is done for each point like this, but it's entire scaling in the same way for the entire points, because x tilde and y tilde are the center of mass of the entire set of points. Actually, this is a linear transformation. And what you do in practice, you take the original problem, you introduce the normalization, which I called here x tilde. It's given like it here, and you solve this problem And then you move from the calculated P tilde by the normalization to the problem that you want to solve, actually 2P. I guess that anybody who took the course in computer vision is familiar with such normalization for fundamental metrics, etc. But this is not an option. This is what you need to do when you solve the DLT problem. This is very important. Any question before I'm moving on?
How do you choose the S again? Can you?
For example, you can choose S in the sense that if you take the center of mass, then you choose S such that the standard deviation of the points would be 1 in direction X and direction Y, for example.
Thank you.
Okay, now we are going to speak about the second part of the resection problem. We already know P, and we would like to get out of P the calibration matrix K. Okay, how we are going to do it? That's what we have. We have P, and we would like to move to here. So the way to do it, anybody has an idea how to do it? I'm sure you're familiar with the kind of decomposition. Anybody heard about the QR decomposition?
Yes.
Yes. Okay, good. So, okay, what is the RQ decomposition? You have a matrix, which is square matrix, and you take the matrix, which is and you decompose it to an orthogonal matrix multiplied by triangular matrix, like what's written here. Okay, this is the triangular matrix. This is the orthogonal matrix. It can be done to any matrix which is square matrix. Essentially, there is ambiguity in the decomposition, and the ambiguity can be removed by requiring that the triangular matrix, like this, have on the diagonal positive entries. Okay? And we are going to use this to resolve the ambiguity, but I'm going to change the notation such that will be more convenient for us, because I want to say the following. R, which is considered to be in the RQ decomposition triangular matrix, I'm going to call it K, like what we are used to. And Q, the orthogonal matrix, we are going to call it R, okay? So A is going to be like what we would like to have, K is time R. So in order to do this, do you have now any idea what we are going to do now? What block of P we are going to take in order to do this?
The left 3 by 3.
Good, great. The left 3 by 3 is going to be our block A, and we are going to decompose it. Good. To K and R. Okay. So we take, in MATLAB notation, it's written like this. And let's decompose it to K times R, okay? So let's write it in an algebraic manner very, very easily. So A 3 by 3, I know the values in A. I don't know the other decomposition. Each row is written like this, A1 transpose, A2 transpose, A3 transpose, right? And I'm looking for A, B, C, D, E, and F. I know that you see here 6 degrees of freedom, and I mean to understand why. And I want to also to get a rotation matrix. Each row in the rotation matrix is written Ri transpose. And if I'll multiply this set by this block, I get for the first row this result, and this result. So in order to solve it, we'll start from the last row. Okay. Okay. So the left-hand side is known. It's A3 transpose. I know it from the calculation of the DLT. Now I would like to extract F and R3 transpose. So if I'll take F to be the norm of A3 and R3 to be the third row divided by the norm of the row, then I'll get F, which is greater than 0, and a row of the matrix which has norm 1. So far, so good. Let's continue. Okay. Now I'm looking on the second line. I'm looking here. This equal to this. And I'm multiplying this row by R3. And under the assumption of that R2 that I don't know yet and R3 are orthogonal, I can cancel this out. And I get that E is going to be this relation. Okay? I know R3, I know A2, I can solve for E. Okay? I'm moving on. Now, I can, from here, determine by the same way that I did from the first line, I can determine D and R2 on the same way that like I did before. Because this is known already and this is known already, I can do the same trick as in the first line. Okay? So I'll continue here. By multiplying once by R2 and once by R3, I can determine B and C. Okay? And lastly, by the same trick that I had in the first, I can determine A and R1. Now, you can ask the question, why are you sure that you get an orthogonal matrix? Why are R1, R2, and 3 are orthogonal matrix? And the answer is that if you follow the construction and you make the calculation, you immediately see that you get an orthogonal matrix. Okay? So just a minute. So this is the way that you calculate the calibration matrix. Okay? And if F is not 1, you can divide everything by the value of F. It does not harm the camera matrix. And you get F, which is 1, and exactly then you get a calibration matrix with 5 degrees of freedom. So we just finished with the resection problem. We have 2 steps, and I remind you not to forget to normalize when you calculate the camera matrix. Okay. Let's move on. Now I want to speak about camera resection in the Euclidean space. I guess you understand that so far we spoke about a general camera matrix, right? We spoke about the camera matrix in the projective space. Is this clear? That I want to move now the camera resection in the calibrated space, in the Euclidean space, calibrated camera. What is the difference? What I would like to understand now? Any ideas?
The location of the camera in the real world?
Exactly. The location of the camera and rotation and translation of the camera with respect to the real world. Exactly. Yeah, exactly. So I would like to extract R and T, actually. Okay. So if somebody is familiar with Ransack, I would like to say that the same couple, Fisher and Bowles, from the Ransack algorithm, invented very nice algorithm, which is called PNP, perspective endpoint, which allows you to take 3D points in the world and 2D projection of the 2D projection of the points in the image and the correspondence between them, and you can get the rotation of translation of the matrix. Sorry, of the camera matrix, sorry. They showed it for n, which is any n greater than 3. We are going to focus on P3P when we use exactly 3 points, okay? So the situation is the following. I have the 3D points in the world coordinates, for example, for this cube, and I have the correspondence, which I mean I have the projection of these 3D points onto the image in local coordinate system. And from this, I would like very much to understand how to extract the camera metrics, how to extract RNT, okay? What does it mean? Okay, let's try to focus on this illustration. So this is the camera center. I have some camera center. This is the camera center of my single camera that I have. Somehow I have the measure of 3 points in 3D world, P1, P2, and P3. Somebody use laser scanner, I don't know, and I know how to measure the 3D coordinate of 3 points in the world. Also, I know to measure the distances between them. And I know that P1 is projected to I1, P2 is projected to I2, P3 is projected to I3. And I know the coordinates of I1, I2, and I3 in the image coordinate plane, okay? Also, the relation between I1 and P1 allows me to I would like to say what is the line of sight from the camera center to the point in the 3D world, and from the camera center to the other point in the 3D world, and from the camera center to the second point in the 3D world. So far so good. What I know P1, P2, P3. I know the distances, E12, E23, E31. I know I1, I2, and I3. Okay, and I know the direction, I1, I3, and I2. And since I know the directions, I can also know the angle between the direction, the angle between I2 and I3. Sorry, L2 and L3, direction between L3 and L1, etc., etc. So here I wrote what I know, just to it will be clear. And now I want to use this information to calculate what? To understand what is the distances between the center of the camera and this 3D point. Here it's written D1, D2, and D3. Okay? Then you will see if I know this D1, D2, and D3, why it's possible to understand what is the camera metrics. But first of all, I would like to calculate D1, the distances between the camera center and the point in the world, okay? And the way to do it is to use the cosine law of the triangles, okay? So the unknowns here are D1 and D2 and D3, right? Written here. As I told you before, I know the angles between the line of sight. Theta 1, 2 is between 1 and 2, the line 1 and line 2, etc., etc. And I know the distances in the 3D world. So take, for example, this, okay, triangle, for example. So it contains dt and d3. For example, this equation comes from this triangle. Okay, dt squared, dt3 squared, minus dt2, d3 times the angle between the line of sight equal to et through t3 squared. This is known. This is known. This is the unknowns. Okay, is it clear? Okay. Any questions? Okay, so let's continue. So I have polynomial equation, 3 polynomial equation. Each of them I got by cosine law for each triangle. Actually, it can be solved, okay, by solving a system of quadratic polynomials. And actually, we know that this system was investigated, and this system has 8 solutions. Part of them are complex solutions. Only of them yield, 4 of them yield positive distances. And actually, to resolve the ambiguity and to take the unique right solution, we need to introduce another force correspondence. But now I would like to ask you a question: how I can move from knowing D1, D2, and D3 to understand what is the camera metrics between the world and the single camera that I have. How I'm going to understand what is R and T? Do you have any ideas? What gave me D1, D2, and D3? What it gave me in our
The point 3D.
exactly. D1, D2, and D3 actually gave me P1, P2, and P3 in terms of the local coordinate system. Why is that? Okay. We had before P1, P2, and P3 in terms of the 3D global coordinate system. That's what we had. This is the world coordinate. Now having D1, D2, and D3, if this is the origin of the camera, I can say that I have what we call P2 prime, P1 prime, sorry, P3 prime. Exactly. That's what I have now. So having this, I have now the 3D point from the point of view of the 3D coordinate system, the global coordinate system, and P1 prime, P2 prime, P3 prime of the same points now in the language of the local coordinate system. Okay? Is this clear?
Isn't it only gives you the translation? What about the rotation?
Just a minute. Good question. Very, very good question. I want to answer to your question. Next slide. So we would like to move from the word to P1 prime, P2 prime, P3 prime. Exactly. We have this. In the beginning, we calculated this. What we are going to do with this? Very good question. So we are going to calculate exactly R and T. And we are going for this to use what is called the orthogonal Procrustes problem. And the orthogonal Procrustes problem say the following. If you have a set of points that you know them in any dimension, and a set of corresponding points in the same dimension, and you know that this point, this set of points is related to this set of points by some orthogonal matrix with no translation, then it is very easy to calculate which matrix transforming from A to B or from B to A. I guess that no outliers, maybe there is noise, but no outliers, okay? Then it is shown, not here, but in general, by Procrustes, that actually, if I have a set of point A and I would like to move to B by some orthogonal matrix, I mean that this is the constraint. I would like to get an orthogonal matrix or rotation matrix, and I would like to move from here to here by minimization of the Frobenius norm between the set of points. I would like to take A, to rotate, and to move to B. Then the solution is exactly using the SVD. I'll take A transpose multiplied by B. I'll make SVD to this matrix, and I'll get that the exact solution to this optimization problem is UV transpose. I mean that I omit the middle matrix, and I'll get that this is the solution. This is actually a closed form solution. Even though the problem is not convex, it is possible to show that the optimized solution to this problem is exactly UV transpose, which is determined by the SVD of BA transpose. This is if I do not have any translation between the two sets of points. If I have translation between the two sets of points, there's also a solution.
Can you explain again?
Sorry?
Can you explain again why we would like to solve the equation of argmin of this?
Yes, sure. Recall that what we had before Just a minute. Okay, what we had before is the following. We had as input P1, P2, and P3. What we had, and we calculated using the cosine law, the P3P algorithm. We calculated the coordinate of the same point, but now in the system, in the local coordinate system. So in order to move from Pi, to Pi prime, I would like to calculate R and T, right? So I would like to explain now, when I have a set of points and another set of points which are related, for example, only by rotation, without the translation, just for now, I would like to say how to move from one set of points to the other set of points. Okay? And this is done using the Procrustes algorithm, which says that here you have a set of points and another set of points, and you know that they are related by some orthogonal matrix. In order to solve it, okay, would like to take A and to rotate it, and then to move to be as close as possible to B, under the situation that we are looking for a matrix Q, which is the unknown, such the matrix Q is an orthogonal matrix. And I said that this has a closed form solution, even though it's not a convex problem. And the closed form solution is made by taking the SVD of BA transpose, omit the middle matrix, and get this solution. This is, I'm not showing why is this the solution, but I'm just saying that this is a solution. Is it clear now?
Yes.
Good. So let's move on. But in practice, I have also translation. So what I'm going to do, I can let you have the report made by Olga Sorkin and Michael Rabinovich that explain very nice how to do this. If you have also translation, not just rotation. So they say the following, and they show that you take Pi and Pi prime, okay? And you take the center of mass of each of them. By the way, maybe it's a bit confusing. Here, Pi and Pi prime is not cameras, it's just points. Sorry for the confusion. Okay. Point in 3D, right? Pi and Pi prime, and you take the center of mass for each of them. You subtract the center of mass for each of them. And then you do the calculation that you did before, and then it can be shown that the translation is this one. And then you are done, okay? So you have all the way to understand how to solve the resection problem in case of the Euclidean space. So first of all, you calculate the distances, and then you have, when you have the distances, you have the correspondence in the 3D space between the point in the global coordinate system and the point in the local coordinate system. And then by using Procrustes, you can solve exactly, and you can get the camera matrix. Okay? Any questions? More questions? Is it clear? I guess I'm not sure. Yoni, do we have an exercise with the DLT algorithm or the P3P algorithm? I don't remember. Do you remember?
I'm not sure. I think that with the DLT we have, but not with the
Not the P3P. Okay. I think I don't have time to cover some recent material using deep learning to find the position of the camera, but I think it's very easy to follow. So we will have the slide and you can follow it. It's very easy to follow. It's not a very recent algorithm, but it's a nice algorithm to be familiar with. Do you have any questions for today? Okay. Okay, so let's finalize the class, and I'll be for your assistance to get a way to write through the model and to get access to the model. And any question regarding the exercises should be raised through the Moodle, to the forum. We'll take care of it. If you have anything to say, this is the time. Other than that, we are done. I'll let you have the slides today. See here something. Do you have any recommendation on where we can read more about today's material? Yes. Nadav, what kind of topic from today's topics you would like to read? Just everything, or? No.
I just will appreciate it if you can refer us to where should
Okay,
we
because
look
you
for.
know, it's kind of just
There
different.
were a lot of topics today.
That's
So,
it. Yes, that's, I'm not sure what
This is why
was.
I'm asking, because I saw Olsen notes which you recommended before, but
It's not
I
there.
saw
It's
that
not
it's
there.
not all covered there. So
Right.
this is why I'm asking.
Okay, let's say the following. I can let you have some material. I can put in Moodle. Okay, let's do the following. I can put in Moodle some material regarding the P3P algorithm, and then I can put in Moodle some material regarding the Procrustes algorithm. And what else can help for help?
maybe chapter 7 in Hartlin-Zisserman.
Maybe chapter 7 in Hartlin-Zisserman, but it's, you know, it's a lot to cover, but I'm encouraged to do this.
And one technical question, the Moodle, when we ask questions, so can we see each other's question?
I hope so. I hope so. Yes, otherwise it won't help. I'll try to resolve it.
Yes, I think that for now you can only ask a private question, but we will try to open a public forum.
We will change it. We'll try to make a forum that anybody can see any other question. If you want to ask a private question, you of course can do it. This is no problem. This is already there.
Thanks.
Okay. So as far as I understand, next time Ronen is going to speak, right? Ronen, are you here? Not sure.
Ronan
Okay.
is not here. Yes, it's Ronan because it's not me. So yes.
Okay.
Not here.
Okay.
It's Ronan.
Okay. Okay, so feel free to ask questions in the Moodle, feel free to send mails, feel free to cover material, no problem. I'll let you have anything that can help you. Okay, just feel free to be in touch with us. I know it's a heavy class today. I know it, but I think that from time to time, it seems that it cannot be very easy to follow, but if you follow the lecture today and you understand or grasp most of the things, if you follow the slides and the talk, you will be able to